Good afternoon, everybody. Thank you for coming in. So Tomas right here and myself are going to spend the next hour or so with you talking about how we built MLflow, the reasons behind that. So to get started, MLflow is a platform for management of the complete machine learning lifecycle. So a quick overview of the details of this talk is I'll spend a few minutes talking about the ML development challenges that you all see. And how MLflow tackles this. A few of you, or quite a bit of you, must have attended Matej's keynote talk yesterday. So I'm going to try and have a little bit of overlap, but not sort of complete coverage of all of that. And then we'll talk about each of the machine components of MLflow in details, and then over the entire two sessions, and then give you some tips on how to get started with yourself on MLflow, using it, contributing to it. It's an open source project. All right, so anybody who's done machine learning in some shape or form knows how complex that process is. So to tease that out, here's a standard flow of how you would tackle machine learning problem. You'd start with your raw data that is stored in some storage, do your data preparation, featureization steps, train your model, and then deploy it to some deployment environment. It looks fairly straightforward. But there are several different complexities that arise when you sort of process these problems altogether, right? First of all, each of these have several tools, starting from how are you going to ingest all of that data, how are you going to store it, into data preparation steps, what sort of tools you're going to use for ETL. And then the training, there are several different frameworks and algorithms that are available for training and deployment, depending on whether you're deploying it on your phone or on a local machine or on the cloud somewhere. There's various different ways of deploying it. And there are, unlike most software development, where you sort of take one tool, whether you're developing a transactional system or a website that has high traffic, you take the best technology that is available and you build your tooling on top of that. Unlike that, machine learning, you want to try out various different tools that best suit your problem. So you might want to try out XGBoost, and you want to try out MLlib, TensorFlow, so on and so forth, right? That's one significant challenge that makes it complex. The second problem we run into is tuning. Various different steps out here require several tuning, experimentation using various different parameters, experiment with different feature windows. And that sort of adds on to these iterative steps. And pretty much the biggest problem arises here. You have to keep track of what you're experimenting with, right? These takes days to train, so you want to see, okay, I used a week training window, and I used this particular framework, and I used these parameters. So there's a whole bunch of bookkeeping that goes around with this. The third problem is scale. As your data increases, and most problems that involve web scale traffic, transactional traffic, generate a lot amount of data, you want to use pretty much all the data that is available to you to get the best result. Scale arises from storage of that data, processing all that data, training are and obviously there's scale amount how you deploy a model. Whether you deploy it on a scalable web service or your phone, there are challenges with designing that scale problem. The fourth, an interesting one, is exchange of models. And in this case, models here could be, your data could be a model, how you actually write your ETL could be a model, so to say. But how is this information flowing between teams? Now, necessarily in most big organizations, when you have different teams working on different aspects of this problem, you'll run into an issue where you have a slight change in one step or the other can cause a ripple effect in downstream steps. Here's an example. If a storage format is changed somehow that causes a delay in your feature computation, can have a trickle-down effect on your performance of your model that is deployed. And the fifth and final thing is governance, where you might want to sort of keep track of everything that you've done, all the experimentation. So at some point of time later, you want to go and audit your particular model from 3 weeks ago with a new data set and using the exact same parameters that you've used. You want to produce that experiment, and the new data should pretty much show the similar results if the model is well trained. So keeping track of all the information, making sure that there is some diligence in storing all the parameters and all the algorithms and versioning of your source code, all of that goes into governance of your model, and that creates the next problem. As we look at this, we started talking to some of our customers, and the codes that we got were pretty interesting from that perspective. So this one particular chief scientist from an ad tech firm says that they build hundreds of models a day to lift the revenues using any library that they can find, right? MLlib, PyTorch, anything that gives them the best results. However, there is no easy way to see what data went into a model from a week ago and how to retune it and rebuild it. So that goes back into the governance and the rerunning of the model and producing the exact same results. Another example from a large consumer electronics firm says that they have hundreds of teams working on machine learning worldwide. However, they can't share the work across different teams. That's a common problem that you've seen. And the problem they run into is that they often can't reproduce the same results. So they can't share codes. It doesn't even give the same results. So that becomes a problem when you want to sort of run the similar experiments and share code, write the algorithms that are usable between teams. So we took a quick look around what are the other players in machine learning are doing. I have used some of these products. So when we started looking at how this works, one of the things that worked best was they standardized on the data preparation and the training and deployment loops. What this means is that the team had several teams that had built the training pipelines, the model development, the algorithms pipeline, and it worked great when you're within those teams and in those companies that work with that. However, if you want to use a new algorithm or a new framework, let's say you want to build in a fresh version of TensorFlow, it's really hard to sort of hook up a new tool into it and a new framework into an existing platform that serves your machine learning framework. The second problem was these tools are available only to engineers within those companies. So if you want to go and try that, there's no way. So if I want to have a clean path to doing an end-to-end machine learning, you have to reinvent those tools. So when we started looking at what was the best way of developing a new platform, the first thing that made sense was building it in an open manner. So that would, such that we can leverage all the benefits that is available to all the engineers in these big companies, and also do away with some of the drawbacks that was available, that was due to getting constrained with a fewer set of algorithms and constrained to a particular platform. So what does that mean to develop an open machine learning platform, right? The first thing we wanted to make it such that you should be able to use any language and any framework that is available out there. So the way this was brought about was through a very clean API interface for various different components in MLflow. And we spent a significant amount of time building those APIs and those interfaces layers between these components such that you can plug and play any of your modules in there to sort of train with, if you like R, if you like Java or Python, you should be able to use those languages with any framework that you are comfortable with and still reap the benefits of MLflow. The second one was a run defined as a particular run of a machine learning flow that you're doing. You should be able to run that in any way on your local, the same way on your local machine as on the cloud. So a mechanism to wrap up your code in such a way that it is reproducible on your machine and then with much bigger amount of data on the cloud, on any cloud interface, in any cloud infrastructure. And the third thing was an ability. We wanted to design it such that it was easy for one person, a data scientist in any small company, to use, but it also scaled to thousands of people in an organization. So if you have thousands of people working on machine learning, it should not be a bottleneck. It should be the same way it works for one person. So to get into the details of MLflow, it was designed with 3 big components in mind, right? And the way it was designed around 3 basic things with tight interfaces between them, such that you could plug and play, use one or multiple of these components, whichever one made sense. So at a very high level, these components involve a tracking server, right? Very simply defined, and we'll go into the details of what a tracking server is. It gives you an ability to record and later on query all the experiments that you've done in your machine learning deployment, and record what code has been used, what configurations were present, the system configurations, what parameters and hyperparameters we used, what were the results, the metrics, ability to store your model, a way to snapshot your data that is available. So everything that is relevant to your one run of a machine learning flow, and store it. And then later on, with a UI that is tied to the same API, be able to query the stuff that you have recorded before. So in a way, it's presented, and we'll go look at the UI, that you should be able to go and see that, hey, 3 weeks ago, I had run this experiment that gave me the best result. What were the parameters that I used? So that I can take that and reproduce it with the exact same parameters. The second 2 components, we covered them in the second part of this talk, and that's projects and models. Very quickly defined, projects is a way to reproduce your runs, a packaging format such that you can sort of wrap up all your code in a way that you don't really need to know how the code is, hand it over to somebody, and they can run it on a bigger installation with new data and try out new parameters. And the third thing is models, which is a packaging format to be able to, once your training is done and your model is ready, how do you take that and wrap it up into a framework that you can easily serve in any form? So this gives you an ability that, if you're great at developing models, if you have a team of great data scientists that can develop models but don't really have the expertise to deploy those models, you could use MLflow to pull that in and say, hey, I want to train these models. I'm going to use MLflow libraries to store it in a way that I can deploy it on Amazon or AWS or Azure or wherever, whatever framework that makes sense to you. So going into the details of tracking server, here's a little code that shows how it is, how you would sort of record your run and sort of walk through it. You have your model training in the middle that I have just commented out. And you're pretty much saying that, hey, I want to start a new run, and I want to log all the parameters that I am using for this run. And then after the model is trained, I'm going to log some of the metrics that the model has produced. I want to actually create some plot from this model, it's a nice graph. I want to store that as well. And then, since it's a TensorFlow model I'm using, I know that. I'm going to log the exact model, and I'm going to package it and store it as an artifact that I can use later on to deploy. So all of this information that you can see in the context of that run is stored within the context of that run. So as much as you can record, it's all recorded, and let's say you have that code, you try this out thousands of times, everything about it is recorded. It's one thing to show slides, another thing to actually see a demo of this working. So to tease out the demo, what I'm using is a Airbnb. This is the website that has Airbnb listings, and it is a bunch of numeric and categorical features about a listing, zip codes, ratings, number of ratings, so on and so forth. And we're going to use that to sort of predict a price of a rating. So let's get into that demo. What I have out here is, now I'm a data scientist. I haven't done much of it, and I'm going to try using MLflow and see how this works. So somebody told me, let's try a linear model first. So I'm going to use a scikit-learn model out here, as you can see. And it's called Elastic Nets. It's a standard, very simple linear regression model. And the reason why I like this is because it has just two parameters to play around with. It's called alpha, and it's called L1 ratio. And I can sort of run this really quickly and see how it goes. And I'm going to say Python, because it's a Python file, and it's a linear. And it sort of produced some results and said, OK, I've used a standard alpha of 0.1, and it produced some results out there. Now, like most of the things that I have done in my past, I would say, OK, what I'm going to do is I'm going to copy all this data and store it to some file. And I don't remember. I'll probably try to remember where that file is. And I'm going to store it to a file, and then I just keep appending all of my different runs that I do. I'm just putting into that file. But after a while, I might forgot to. I add a new parameter. I start doing some things. I might forget to do things. And I say, hey, I remember I'd done this model a while back. I don't know how to do it. So let's see how MLflow solves that problem. So I take that same code, again, that I had seen. And before I run this algorithm, I'm going to use my handy-dandy macros. And just using the MLflow, I'm going to just highlight some of the MLflow things. So use MLflow log parameter to log this parameter. Log param command to log this parameters that I'm using. So alpha and L1 ratios. And then this model is going to run. And out here, I'm going to log the metrics that were produced out of this. And then while at it, I'm going to log these artifacts that we were talking about. So I'm logging the training data that I had used. I'm logging a plot that I had created. And I'm actually logging the model because, again, I know this is a scikit-learn library that I had used. And this model is a sklearn model. So I'm going to use a special wrapper inside MLflow to wrap it up as a scikit-learn model and save that associated with this run. OK. So let's do that. And let's start off with something like Python linear. Oh, I forgot that I need to sort of give it some constants. So I'm going to try out a bunch of different values for L1 ratio and alpha. And then I'm going to kick off a UI to sort of see how these things are getting recorded. OK. So as we've all these different things that we've tried out, what we have is things that the runs that we've made so far, they've been recorded. We've recorded the alpha values. We've recorded all the RMSE values, and so on and so forth, right? And then we can sort of sort it up and down. But I don't know if this is necessarily a good result that I have received. Why don't I use some simple poor man's hyperparameter tuning mechanism where I'm going to loop over multiple values for each of alpha and L1 and then see how that performs over time, right? So I'm just going to run this script that is just taking on multiple values of alpha and L1 ratio and then just run this script multiple times. And the beauty of it is now it is recording everything as we speak onto this. And I can sort of see as it is sort of in real time how it is populating this data and pushing this data onto MLflow Tracking server, recording each and everything. And so every time anybody who's sort of pushing it to this server can sort of do that, and all that data is coming here. The one thing I want you to sort of see here is everything that is recorded about this is which user is sort of doing it. Now it's just me. What source file was used. What is the version control? Because I'm using Git underneath, what is the version control that was used for this file? So let's say at some point of time I edit it. It's logged in Git. I can go to that particular file and say, hey, I had used these parameters, and these were the best metrics that were that I achieved with this, and I want to be able to go back to the exact file in Git. So it sort of pulls that from Git repository as well. And then I can sort of play around with this a little bit. I can say, OK, I think R2 might be a little significant. It's sort of going in a few values. So what I'm going to do is I'm going to sort of search such that R2 values is less than 0.25. just so that I have to, oh, great, and I have an error. All right. So R2 values are between in this, so I can now, I know that this is a valid range that I'm looking for. And then maybe I can look for the least value of root mean square error. This seems to be around the same value. And for some reason, this for a range of parameters, this model seems to be doing just fine, all this. Now, I can also go inside this directory and sort of go a little bit deeper and sort of see how this is doing. So these are the values that have been recorded over time. As I mentioned, we have this data that is stored. Now, when I'm running this MLflow server, I'm running it on my local machine. So you'll see the path on my local machine. If I were kicking it off on a cloud, you'd see the path for the cloud and how to get to it. We logged a plot, so you can see a plot out there. The model, I mentioned that we were using a specialized scikit-learn library to do that within MLflow. So it sort of logs it like a model. This is a pickle file. And then this is some kind of data around the model that is squirreled away here that it can now load that model back in. All right. All right, so one other thing I can sort of do with this is I can try out another library. So I have a TensorFlow library that I had been using and something experimenting with before. And again, I have MLflow recorded, and I'm doing something a little interesting. I'm using the hooks API for TensorFlow trained to sort of periodically record this metric over time. So after every few iterations, it's going to go do the metrics and record it and push it out there. So I'm just doing this and using the logging API to do that. So I don't really have the last metric. I have metric throughout time. So I'm not going to kick this off because it's going to take some time to run. I'm just going to restore it from backup I had run before. And let's go see how those runs look like. And this is looking a little bit more interesting. If I sort it on MLflow on our MSE, I see that a couple of runs of TensorFlow have done a little better. So I'm going to click on that, and oops, this is great. Okay. I'm going to fix this offline, not really fix it inside in a demo. But, all right, so what I wanted to get to is I can now go and look at how these models are performing over time. And I might have a picture that is saved up somewhere. I can probably go and debug this and see what is happening. And then see if a model has dropped performing over time and see where it is and debug it and stuff like that. OK, let's go back to our presentation, if I can find the window. Sorry, folks, give me a minute. All right, so let's go back quickly to our presentation where we left off. OK. So what we have seen so far is your MLflow tracking server. And in this example, I showed you from a local machine. I have tracked this API onto MLflow. And then it's recorded inside the MLflow server. In the same way, you could have some other local apps or cloud jobs push data to your tracking server. And then you can write API yourself, or you can use the UI that is available to you to sort of query the server and figure out what happened and which run is best and share data across teams and so on and so forth. OK, let's go and quickly look at the key concepts in the tracking server. We saw that we have all the experiments that you have stored, that you've run. An experiment can be mapped to a particular MLflow project that you're running. Parameters are various different parameters that are used in your training run. Metrics are, again, metrics that are computed out of your model flow. tags and nodes. You might want to, at some point of time, let's say you've run hundreds of different runs and want to sort of store some information about a particular run. You want to have some notes that are written in. So the UI stores that. I didn't really get to demo that part yet. Artifacts. Artifacts are, again, all sorts of data files. You might want to store some plots. You might actually store the models that are involved. All of that are as artifacts, and that can be stored as well inside the tracking server. What source code that you'd run, what version you had run. So all of these are just, again, a quick revision of all the stuff that we had seen so far. Now, in this example that I showed, I was using a local server running on my Mac that was storing all the data. So for entities, we have the local file store, and entities is going back to your metrics and parameters and so on and so forth. So you could have a local store, or you could have a database backstore. So depending on how big your organization is, and when we have a hosted version inside Databricks, we have a database backend store where all the metrics and parameters are run such that you can quickly query through those. But for your artifacts, the big models and the data snapshots that you're using, we have a few that are available. There is a S3 back store, there's an Azure Blob store, Google storage, there's a Databricks file system abstraction on top of artifact repo. And these, interestingly, a lot of these have been contributed by open source. So I wanted to make a quick thank you to the open source community that has contributed to this project and sort of added all of these different APIs to be able to record these artifacts to Google and Azure Blob stores. Before we break for time, I wanted to just quickly show that, again, this is an open source project. A call to action is anybody, if you're using a simple, if you're trying out machine learning for the first time, or if you've been doing machine learning for a while, I recommend you try this out once. You can either use PyPy to load MLflow, or you can download it out of GitHub repository. So go to mlflow.org. There's a whole bunch of examples out there. I would try this out. Send us Slack on the Slack channel that is available, or open raise issues and send patch requests on GitHub. So. I'll leave the slide on for a while for you to sort of to try it out. And before we break, if you have any questions, we have like 3 or 4 minutes. Yeah. Nick.
Oh, there you go. So I actually have 2 questions. So what happens if you don't commit before you run the experiment? You still see the Git hash from the previous version, not the version which is actually used.
Yes, that is a good question. We've been getting that question from the open source community as well. We have been thinking about what is the best way to do it, whether it makes sense to sort of stop you from doing that. Does it make sense to sort of recommend pushing it to a remote local branch? Or does it make sense to actually take a blob of your diff and store it as an artifact? I mean, all of these have different repercussions, access issues, and stuff like that. So it's out there. We could try those. It's one of the things that we are sort of openly. And if you there are a few questions out there on GitHub for it. Please feel free to chime in on there as well.
The second question will be: if you store large data, such as the training data,
yeah.
Is MLflow smart enough if you're using the same data across multiple runs to just make a symlink to the previous version, or does it make hundreds of copies of the same data in the repository?
That is a good question. Right now, the way we have implemented is just through APIs. So right now, there is no logic behind the server to sort of say, hey, this has been recorded before, there is this access control. But that's something that is in the works as well that we're considering. Yeah.
Hi. I wanted to ask, in the code that you just shown, you had a load data method for the Python file.
Yeah.
And I saw that in there you just dropped the label column, but potentially you can have like a little more advanced, like even some feature engineering that you'd want to include in the model. In that case, I mean, when you save the model in a certain flavor, you save at the moment, if I'm not mistaken, the model itself. And when you serve it, you serve the model. Are there any plans to incorporate the feature engineering part into the model as well?
Yes, that's a good question. So the way we can have defined this is, and there is an example that Tomas will do, time permitting, with doing a multi-step flow, where you have a step, and then the following steps are depending on the previous steps. So there is, again, an example for multi-step flow on GitHub open source as well that you can sort of try it out, where you do feature engineering and then you try out an ALS matrix refactorization and then a TensorFlow. So there is example of doing feature engineering as well. And to go back to your previous question about using a particular label and stuff like that, that is a good question. We haven't thought about customizing inside MLflow with that. If you look at it, the amount of code for MLflow that I added was very little on your existing stuff. So that can be thought of as a new API that we can define to sort of surface out what it has done. In the model that was stored, it had stored some values and things like that. That can be an enhancement we can add on top as well.
Hi.
Maybe
My question is about logging the model performance during training. So what if you want to log some more detailed training statistics, like say some learning curves? Then how would this be possible? And is there plans to, in addition to this kind of statistics, is there plans to incorporate some deployed model performance tracking and kind of visualization of them on the same grid?
Yeah, again, a very good question about the serving side of things. So what we have talked in this session is about the training and tracking of that data. Some of the stuff that Tomas will cover is, once this data model is trained, how would you serve it? There is a lot of ongoing work that we are doing at Databricks about the serving side of things. Specifically, once you have a model in production, how to sort of having a similar API-like flow to sort of get data about what were the parameters sent for a particular call? What was the prediction? How accurate was it? What time it took? So getting all of the metadata around it is something that we are working on in the near future. So in future Spark Summits, you might see a talk about that.
That's time for the first half. We'll start again in about 6 minutes for the second half, so there will be more time for questions if you stay. But thanks, everyone, for joining us. Let's give Manny a round of applause. All right, everyone. Thank you for joining us for the second half of the MLflow talk. Here's Tomas to kick us off.
Hello, everybody. Welcome back after the break. So in the first half of the talk, Manny gave sort of introduction to MLflow and dived into MLflow Tracking. And I'm going to follow up on his talk by giving more details about the remaining two components of MLflow, which is projects and models. For those of you who might have missed the first talk, don't worry, it's not really a prerequisite. This talk should be sufficiently self-contained. Right, so let's get to it. Okay, so this is the outline of the talk. I'm going to start with MLflow Projects and then follow up with MLflow Models. Both parts have very similar structure, so I'll first give a motivation for each, explain why we think these projects are important. Then I'm going to talk about how they are implemented and what you need to do to use them. I'll show some examples, and then I'll wrap up each section with a demo demonstrating the capabilities. So MLflow Projects, why do we think that we need something like this in current, in current machine learning environment? So as I'm sure all of you know, the modern machine learning landscape is very diverse, and there's like many different tools. So you have PyTorch and XGBoost and TensorFlow, and the list goes on. And there's so many tools. And on top of that, you have data scientists who might want to be running these tools in different type of environments, right? So they might be running on laptop, and eventually they might need to push their code in production, and it's like yet another different environment. And so the outcome of all this is that we have a diverse set of tools which needs to run in diverse set of environments, and it's really difficult to ensure that our code can run in all these environments, and on top of that produce consistent results. So this is how MLflow kind of envisions tackling the problem. MLflow project is kind of a wrapper or like a packaging around your machine learning code, and it includes both code and data and configuration needed to run the project. And then on top of this packaging format, we have APIs which allow you to execute this code either locally, whatever your local environment might be, or remote in the cloud. Right, so this is kind of a wrap-up of what MLflow projects are. So it's a packaging format for reproducible machine learning runs. The first principle of MLflow is kind of it needs to be easy to use. It needs to be easy to get into, because we don't expect people to like drop everything what they've been doing and move their workload to MLflow. So any code folder or Git repository is already ML project. You could include optional ML project file with additional configuration, which we definitely recommend to get the most benefits. But to get started, you can just execute any GitHub repository. MLflow project defines dependencies for reproducibility, which is really important fact, because oftentimes different versions of libraries give you different results. Sometimes it may be even difficult to figure out what configuration the original person ran their code in. So we include the description of all the dependencies the project needs to run with the project. And then, as I mentioned earlier, we have execution APIs for running projects locally or remote. And the APIs are both in CLI and the current 3 clients that we support, which is Python, R, and Java. And I'm going to show those later in examples. Now, how does MLflow project look like? So it's essentially a directory structure. You can see here that we have some configuration file, then we have some conda YAML file with dependencies, and then two files with code. In general, there could be more things. This is a simple example, but it's going to be similar layout. And then the interesting part is the ML project file, which is the configuration of the project. So you can see that on the top it lists the conda YAML file, which defines dependencies, in this case conda dependencies. And then it has a section for entry points, which lists all callable functions or callable programs you can do with this project. And you can see that in this case there is only one entry point. It's called main. And it lists its parameters, and later on it gives a command which you need to execute. And in this case, it's kind of simple. You just call Python main.py, but in general it might not be that simple to call other people's code. Everybody uses their own argument encoding scheme or different languages. So the ML project kind of gives you uniform API to execute machine learning code. Now here's examples how you would execute this project. Okay, so this is it for quick overview. Let's get into an example. So I'm going to follow up on Mani's Airbnb data science quest to predict prices of Airbnb listings. And in this hypothetical scenario, we have these 2 data scientists who collaborate on this project. And Erin used XGBoost in Python, and Amy used Keras in R. And they want to collaborate and get the best result to submit to their boss, right? So they're sharing the same MLflow server, and we can see that they both submitted a run. We can check all the parameters they had and the metrics. So in this case, we're optimizing on RMSE, which is root mean square error. And we have a value for training set and test set. And we can see that Amy's code seems to be doing way better, but we're going to investigate a little bit further. Other interesting part here is that you can see that the source is a link, and if we click it, we go straight to the GitHub repository. And it's because this project has been run from Git, and I can see what exactly ran. And then let's check her code, and it seems a bit complicated, especially to maybe someone who's not used to R, and it's not immediately obvious how you would run this code. But if we go back to MLflow, and get a detail of the run, you can see that there's a command line actually how to run this thing via MLflow. So let's give it a try. So I can simply copy paste this code, and you can see that there's no magic. I just put in MLflow run, the link to the GitHub project, and then I specify the 3 parameters that this program has. Okay, and MLflow is fetching the project from GitHub. We'll run it, and then I can see if I indeed did get reproducible results. So we have a new result here, ran by me. Easy. You can see that the result is not quite reproducible, but this is due to the fact that if you look at Amy's code, she's using deep learning, and her code is not reproducible by itself. I could do the same to run Erin's XGBoost code, but I'm going to show you how you can execute it from an R client. So maybe Amy looked at the results and she goes like, yeah, my code is doing way better, but I don't quite like the parameters Erin picked for his XGBoost because I kind of know the algorithm conceptually. I don't want to deal with his code, but I can execute it the same way as we just did now with the CLI. I can execute very similarly from using the R client, right? So, she works in R. She's used to RStudio. She can very easily execute MLflow run and execute Erin's XGBoost program with different parameters. And there you go. We have the best. We have the new best result. Seems like it was a good idea. The programming interface is nice because it's way more flexible than CLI, or maybe equally flexible, but easier to use for someone who's used to R or Python rather than bash scripting. And I could use the same to do a simple grid search here. Now let's take a look. Let's take a bit of a look how the project looks like. So here's the R project, and as we saw on the slides, it's just a directory structure with some code. We have the ML project file with configuration. Let's take a look. There is a name and list of entry points, a list of parameters, and a command. In this case, the command might be a little bit more complicated. Like I wouldn't necessarily know myself how to run an R script, but I don't have to worry about it. And for dependencies, we can see that there is a list of R dependencies here, which is similar to Conda dependencies for Python. And one more cool thing about MLflow Projects APIs is that, as I showed on the slide earlier, at some point I will need to supply to provide my code to production, or maybe I want to run too many things or too big a problem which runs for too long. So in many situations, I would want to execute my code remotely rather than locally. MLflow allows you to run your project remotely just with a simple command. So this is a very similar command I would use to run it the same way I did for Amy's code. This time I pointed to the Python XGBoost project, and I say mode equals Databricks. In this case, it will run on Databricks Cloud. And I can execute it like this. So this will automatically package my project, upload it to Databricks, activate the environment, run it there, and log the results. It takes a while, to be honest, to start a new cluster and to activate the environment. So I pre-run a couple of projects so we can take a look how that looks. Oh, wrong link. Okay, so this is a project which ran on Databricks. It has the same metrics, the same results. I can see the logs from the run via a link here. Oh, this is the new run, so the logs are not available yet. Okay, so that's it for the MLflow project. Let's get back to the slides. And let's get to models. So why do we need something for models, right? And the motivation is very similar to MLflow projects. So we have the same machine learning frameworks, the same number of those. But this time, we want to apply them to production. And what that means, well, that can mean many things. I might want to supply some inference code to Docker. I might want to score on big data in batch, in Spark. I might want to supply my code to existing serving tools like Azure ML or the AWS SageMaker. And then what you end up with is this like awful end-to-end mapping where basically you have to provide code to do any of these for any of the different frameworks, right? And it's not very sustainable. So what MLflow envisions here is to create this generic model format which can kind of serve as a proxy, and like all these tools can produce models in MLflow format, and there's going to be implementation deploying MLflow models to all the endpoints. And this simplifies our problem quite a bit. And you can see that we have different flavors which serve to support all the different frameworks and also different endpoints, which I'm going to talk about in a bit. So what is MLflow Models? Similar to MLflow Projects, it's a packaging format for ML models. It is, again, a directory structure. This time there is a mandatory ML project file, which is to specify a couple of things. It has to, well, it doesn't have to, but it should specify dependencies the same way as ML project. It has to specify a list of flavors, which it can support. And I'm going to talk about flavors in a little bit, but basically any model can produce several flavors, and flavors are actually a representation, different representation of the same model. And they can be used in different situations. And similar to MLflow projects, there is an API to serve the models either in code, in Python or R, or Java, or via CLI, and to deploy it to REST API endpoints. So here's an example of MLflow model. You can see that it's, again, directory structure with some configuration file and some model-specific files. In this case, it's a TensorFlow model, so we have an estimator here and a saved model. Now, if you look in the configuration file, we can see that there's some generic information such as run ID, which generated this model and when it was created. And then we have this list of flavors. And you can see that it is indeed a TensorFlow model. The first flavor is TensorFlow and contains information needed to reload this model as a TensorFlow model. The second flavor is a Python function, which is this very generic Python model for which we provide many different APIs to deploy it either to Spark or to SageMaker or to Azure ML and so on. So because TensorFlow can produce this Python function, it can be directly applied to all those things. And here is an example how you would log such model. It's simply you just do MLflow TensorFlow.log model and pass it a model. Right, so I talk about the flavors. So any model can store different flavors representing, I guess, representation of this model for different uses. So for example, Spark ML model can produce Spark flavor and Emily flavor. Spark flavor is great because it can represent any potential Spark ML model, and it can be scored in Python and in Spark as a UDF. Emily flavor has advantage that it provides way faster real-time scoring. By producing both these flavors, Spark ML can provide optimal, or the MLflow model can provide optimal performance in different scenarios. The other motivation for providing different flavors is that we have these generic flavors. I mentioned it earlier with the Python function. So these generic flavors have already a lot of utilities implemented for them, a lot of functionality attached to them. So by generating this flavor, you automatically inherit all the work that has been done. And the last motivation for having different flavors is that different flavors can be loaded by different languages. So your model can be language agnostic, and you might produce Python function to load it in Python, R function to load it in R, and so on. Now here's a closer look on what Python function looks like. So it's intended to be this very generic thing which can represent any potential Python model. So it is just a directory structure. And in the ML model, the only basic limitation here is that the ML model must include Python function configuration, which might specify a module which can load this model, and that's all. And this model will be loaded dynamically at runtime. We will call load model on it, and its contract is that it has to return an object which is a predict function. And this predict function is very loosely defined as it takes a pandas data frame and produces pandas data frame or a NumPy array or a list. Okay, so this is enough theory about the models. Let's take a look how we can put these models into production. So there is many different endpoints, as I mentioned earlier on the slides, where we might want to deploy our models. The simplest one is we might want to predict locally. Right? And it seems trivial, but again, similar to projects, you might not know how to score someone else's model in some obscure language. So let's see if we can score Amy's model earlier from R. Okay, so this is how you can use the CLI to score any model logged with MLflow. I basically, well, any model which provides Python function, to be exact. So you basically give it a run ID and the path to the model, and the port where it's. Oh, actually, I skipped ahead. This is how you deploy it to a REST API endpoint, but I might as well. So yeah, you provide run ID and the path to the model, the port number, and then we can simply start a REST API server. serving the model we generated earlier in R using keras, not knowing anything else. And then I can query the endpoint like so, and I get results. Okay, so I kill the server. Now what I meant to show earlier was actually a simpler use case where I apply the model locally by predicting on a data file, producing file in the standard output. So I can do that. It's the same use case as we just served with the REST API server. And yeah, again, we have predictions, right? Again, like I don't have to know how that code was produced, what frameworks it uses. It's just there. I can use it. Now let me go back to the REST API server. So by doing something like this, I can easily deploy the model anywhere, basically. Anywhere I have running server, which I can access to, and you can use it as a scoring endpoint. We also have plugins to deploy to SageMaker and Azure ML, which can be readily used. Other than that, you are also free to create your own server and use something like this to start serving the model. And the last scoring endpoint I mentioned is to score on big data in Spark. And previously, I ran example on Databricks, and I can see it here, and it generated a model. So let me see if I can score it in Spark. Okay, this is just necessary setup. I'm initiated MLflow, connected to the tracking server, and loaded the data. Now we can take a look on the data, what we're going to be scoring. Okay, so here we have the data set. It's the same data set as we've been operating on. So, it's the Airbnb one. You can see the familiar columns, how many people it accommodates, how many bathrooms, and so on. And we want to generate predictions for this data set, right? And because we already have model, which I could have generated on my laptop log with MLflow, I can use MLflow model interface to generate a Spark UDF. And it's as simple as this. I can call MLflow Python Spark UDF. I pass it the run ID and the path to the model. And I have a Spark UDF. Again, I don't have to know what that Spark UDF does. I don't have to know which framework it used. It's as easy as that. Now I generate our predictions. And I have analysis of how my platform performs over big data. Okay, so we don't really have time for advanced use cases today, but if you check our repository, there is a directory with examples, and it includes 2 advanced use cases. One is hyperparameter tuning. How much time do we have left?
About 5 minutes.
5 minutes, okay. Yeah, so there is hyperparameter tuning, which basically tries to optimize a TensorFlow model or keras model over a data set, using MLflow to, using all the benefits of MLflow we basically mentioned today. So it uses MLflow Tracking for tracking results. It uses projects to encapsulate the code, and it logs MLflow models, which you can then apply directly. And the other advanced use case we have is a multi-step workflow, which comes very frequently in practice because, as you probably know, the data does not come clean. You might need to run some ETL first. Oftentimes, there's some pre-processing needed, which if you are planning to run deep learning on expensive GPU machines, you might prefer to do it on different cluster on CPUs, prepare everything, and then run your TensorFlow training as a separate step. So there is an example which does exactly that, called multi-step workflow. You can check it out and run it. Now, if you guys are interested in MLflow, please check out documentation at mlflow.org. You can install it from pip and start using it. And there is a Slack channel, which we would really appreciate any feedback on. Now, there's an ongoing MLflow roadmap. So, yeah, we keep working on more things, adding new things. Again, we would appreciate feedback so that we know what's in demand.
All right, we have a few minutes for questions in the back.
Thank you for the talk. I'd like to ask whether this also scales well when there is like a million models involved. Let's say we train always a million models at once. Can we access to these models by this framework quickly? How are they stored in the background? What is going on after?
Mm-hmm. Yeah, that is a great question. So it depends what tracking server you use. In this case, if I would use the distributed one, I see the models. It might not have been obvious, but I executed a run. It wasn't ready yet, and it was already showed there. So, that would be independent on how many runs I would be running. So, like all the runs would show here and show incremental progress. And the models where they are stored, it again depends kind of on the implementation. Typically, in deployment, it would be on some sort of a blob store.
Thank you.
Thank you. Will you have in the roadmap an integration, scripting, automatization between MLflow and, for example, Databricks scheduler to have conditions to automatically go back in time and restore previous model? For example, if I have a control set of data constructed each week to test if my latest model had done better or worse than the previous one?
Yeah, so we're definitely working on integrations with Spark. And I don't know if you've seen the talk about integrating MLflow and Delta. It was one of the keynotes. You can probably look up the video. That one has.
Well, I was specifically thinking about scheduling automatization of previous models restoring in certain conditions.
Okay, I see. Well, we might be adding such functionality as it's needed, but currently, right now, we don't see that as a priority because we have so many things to add before.
Okay, thank you.
All right, we have time for one more. Any over there? No. All right.
So for the real-time scoring REST API, I tried creating a microservice around Spark using data frames, and it had a pretty slow latency, somewhere in the range of 500 to 1,000 milliseconds. So have you done any optimizations on latency part in the real-time scoring in this scenario? And if yes, how?
Right. So what did you use for your real-time scoring? Did you use Spark streaming or?
No. Essentially, as soon as a request comes in, I just create a data frame or a data set out of it, and then I run it through the Spark ML pipeline.
Okay, I see.
Yeah.
I see. Yeah, so The Spark models have pretty big latency because they essentially haven't been really built for real-time scoring, right? They're built for batch. I would say the optimization to use in that case is to generate, if your model is Spark model, generate the MLeap flavor. And the MLeap flavor has like 10 times lower latency for scoring, according to our benchmarks. I'm not sure if I understand your question. So there's the latency of the model, and then there's the latency of the server where you apply it, right? And the server where we apply it is like very bare bones, because there's just, if you deploy with MLflow, it's going to produce a server which basically has only one endpoint, and all that endpoint does is it just reads the data and then passes it to the model. So there is almost no added latency on top of the model itself. So then it really depends on how your model is implemented, right? And let's say for Spark models, if you have to first take the data, transfer them into Spark data frame, then generate predictions, and then turn that Spark data frame again in like a usable data that you can return in your REST API endpoint. There's like a lot of added overhead, right? And that's where it goes to. So that's why the optimization here is to use different format for the model, which is the MLeap library. And will basically produce a model which is the same thing. It will read the Spark model data, produce an equivalent model, but remove that restriction of having to create a Spark data frame and producing Spark data frame.
All right. Unfortunately, we're out of time. Let's give Tomas another round of applause.